Problem 20.1. What orbitals are used to form the indicated bonds in alpha synensal? And in what type of orbitals do the lone pairs on oxygen reside? Well, first of all, we have this bond here, number 1. And in number 1, we have a carbon that is sp2. This is an sp2 carbon, and a carbon sp2. They're both sp2 carbons here that make this bond. For number 2, we have a carbon sp2, and or for the sigma bond, we have a carbon sp2 and oxygen sp2, and for the pi bond, that's sigma, we have a carbon p and an oxygen p. Now for number 3 out here, we have again 2 sp2 carbons, so we have csp2 to csp2. Now, in what type of orbitals do the lone pairs on the oxygen reside? Well, those are both in sp2 orbitals. Number 2, which carbonyl groups in the anti-cancer drug Taxol, and this is an example of Taxol here, will undergo nucleophilic addition and which will undergo nucleophilic substitution? Well, a carbonyl compound with a reasonable leaving group, remember a reasonable leaving group will be something like NR2 or OR that is bonded to the carbonyl, will undergo substitution reactions. So let's see, we have this carbonyl will undergo a substitution because we have an OR. We have this carbonyl. I'm just going to underline the carbonyls. Okay, so now I think I have identified all of the carbonyls. This will undergo a substitution because we have an NR here next door in the alpha position. This will undergo a substitution because we have an O in the alpha position. And here, this will also undergo a substitution. We have an oxygen in the alpha position, and here as well. Now this one, on the other hand, will not undergo a substitution. There is not a good leaving group in the alpha position. So this one will undergo addition reactions. So even though it's a complicated molecule, just following the simple rules will allow you to predict whether a group will undergo an addition or a substitution reaction. Number 3, which compound in each pair is more reactive towards nucleophilic attack? Well, remember that aldehydes are going to be more reactive than ketones, so keep that in mind. We have aldehydes, which will be more reactive than ketones. And in a carbonyl compound with a leaving group, remember your reasonable leaving groups, the better the leaving group, the more reactive. So first, let's analyze for aldehyde versus ketone. Here we have an aldehyde, and here we have an ester. So this is going to be the less hindered carbonyl. This will be more reactive. Now in the second one, we have a ketone here, not an ester. And here we also have a ketone. So now we need to analyze this for leaving groups. Remember, the better the leaving group, the more reactive. Also, the less hindered, the more reactive. This ketone has a methyl and an ethyl. This ketone has an isopropyl, and it has an ethyl. So this is going to be less hindered. Less hindered is more reactive. For C, we have a chlorine and we have an ester with a methoxy, really. So what we need to look at then is the leaving groups themselves. So is chlorine a better leaving group than a methoxy, or is methoxy better than chlorine? Well, the answer is chlorine is the better leaving group and therefore will be more reactive. In D, again, we're analyzing for leaving groups. Here, I'm just going to highlight the leaving groups. We have this group and we have this group. Now, the oxygen being more electronegative tends to be a better leaving group, and therefore, it looks like all of the ones listed on the left ended up being more reactive towards nucleophilic attack.